Hello everyone! In this video I will show you a massive neodymium permanent magnet weighing more than half a ton. This magnet, made of rare earth elements, represents the strongest class of permanent magnets. And in this video, we'll first see what happens when you approach it with ferromagnetic materials, like steel, and then afterwards we'll explore how conductive metals behave in strong magnetic field. Here is a wrench and a scale for measuring the pull of magnet, which reaches 25 kilograms, while the wrench itself only weighs 1 kilogram. On larger ferromagnetic objects, attraction can easily reach hundreds of kilograms. Next up is a hammer. Note that I added 5 centimeters of layer of wood so not to damage the surface and be able to easily remove it. Even with this added distance, the pull force is 40 kilograms. Afterwards, a flexible iron sheet is placed to the magnet, which illustrates the distance where objects are visibly attracted. The permanent magnet of such size is stronger than Earth's magnetic field in a radius of about 4 meters around it, and it can turn off screens of laptop from 1.5 meters. Ferromagnetic objects from iron are drawn to magnet from half a meter away, as illustrated with showing the iron sheet. We continue experiments with placing a ferrofluid on the magnet. This reveals the spikes on the surface. These spikes are acting like magnetic field lines, so in a sense you can visualize the magnetic field direction and strength. Sometimes the camera loses focus because of the strong magnetic field interferes with electronics and sensors in the camera. The ferrofluid contains very tiny ferrite particles, which act as tiny magnets, and when the external field is applied, they align in spiky structures pointing in the direction of magnetic field vector. When in close proximity to poles, magnetic forces dominate over gravity, making so the fluid can defy gravity. If I were let to go the container, it would fly towards the pole of the magnet, the spot with the highest magnetic field intensity. Next up, we take a 4 kilogram copper sheet, and when we throw it towards the magnet, it rapidly slows down. When the plate is getting closer to the magnet, it moves noticeably slower. All that happens because of the induced current in the copper sheet. Copper is an excellent electrical conductor, and when it's moved in the magnetic field, the changing flux creates eddy currents inside of it, according to Maxwell's Faraday's law of induction. In short, these currents creates an opposing magnetic field and overall dampens the movement of copper, and that's why it is extremely difficult to move copper sheet next to the magnet. And this simple demonstration perfectly showcases the effect of opposing forces caused by induction. Normally, a plate of such size will fall down in a second. However, since it's placed in a strong magnetic field, it takes almost 20 seconds for it to hit the ground. In the end, for bigger effect, we took a 20 kilogram copper sheet and rolled it in a cylinder, which we dropped on the magnet. The first attempt was with a couple of centimeter gap. The copper sheet is slowed down up until it reaches the center of the magnet. At that point, the magnetic flux becomes negative and current changes direction. In the second attempt, we shrunk the gap to 5 millimeters. In both cases, it is overwhelmingly slowed down by the induced currents and not the friction. Thanks for watching, and if you enjoyed it, you can press that subscribe button for more videos.